Welcome, everybody. Today I'm going to go through the activity that we had at the end of last week's class, which involves a few different resistors. Today's video is going to be a little bit long, so you're welcome to skip forward to the end if you want to kind of just see the result of this exercise. But if you want to kind of see the nitty-gritty details of how you solve one of these circuits, you can stick around for the next few minutes. So just like we did in class, I'm going to give some names to things here. I'm going to write some currents down. So I got some current that's going through the battery, and I got some current that's going through each resistor. I don't know how big each of those currents is just yet, so I'm just going to draw them as generic arrows. I'll call this one I battery. Then we've got I3, I1, and I2. I'm going to draw a quick voltage diagram here. It's very similar to the ones we've seen before. I'll go ahead and throw it up here. So we're going to have voltage gain across the battery. So I'll draw that as an upward arrow. And then I'm either going to drop a bunch of voltage over R3, like so. So I could write this as V3 and this one here as V battery. Or I'll draw this one off to the side. I'm going to have a gain in voltage over the battery. And then I'm going to have a pair of voltage drops. And I don't know how big those are going to be, so I'm just drawing them as arbitrary lengths. And again, in all of these voltage diagrams, you notice that I get back to where I started. Let's see if I can label these ones here. So again, V battery over there, I'm not going to label it, V1 and V2. I usually like to work in magnitudes for these voltages, and I'll assign the sign arbitrarily, and you'll see how that works in a minute. So my next task here is to write down the loop and junction rules. I usually like to start with the junction rule, actually. So I'll go ahead and start there. And I see a couple of places that I want to use the junction rule. One is R1 and R2 are in series with each other. So there's no interesting junctions there. So I can right away say that I1 and I2 are going to be equal to each other. And then the other junction I have is up there at the top of the screen. And that tells me that the incoming current, which is I battery, is going to be equal to the current through 3 plus the current through 1. Those are my junction rules. And again, you'll notice that I'm only working with magnitudes here. So I'm putting the I's on different sides if they're in or out. If I do end up getting a negative result for a current at the end, it just means that I picked the wrong direction. And I have to flip it around. All right, junction rules. Or sorry, no, loop rules. So I'm going to do some loops here. And the loops I'm going to do are basically the same as the ones that you see over on my voltage diagram. And it's really easy, just like with free body diagrams, where you can see what forces are going on. You can see really clearly what the voltage equation is going to be, because that VB that you gain over the battery is going to have to be equal to V3. And the voltage over the battery is going to have to be equal to V1 plus V2. The last step that I need here is Ohm's law. Ohm's law, which we talked about in class last week, tells us that the voltage across a resistor is equal to the current through that resistor times its resistance. So I can actually go edit my voltage rules and say that this is actually going to be I3 times R3. And this one down here is going to be I1 times R1 plus plus I2 times R2. And then I can go ahead and use my I1 equals I2 equation to just make that the same right there. Awesome. So how do I want to go about solving this? Well, my goal is to find the voltage and the current through each resistor. The things I know are the R's and the voltage over the battery, but I don't know any of the currents and I don't know any of the voltages of the resistor. So I need to figure out how to solve this combination of equations. And actually, the easiest thing that I can do is look here and say, I can factor an I1 out. And if I do that, whoops, there we go. You will see that I can write this as VB equals I1 times R1 plus R2. And right away, you might notice, it kind of just looks like when I add those two resistors together, they become a new, bigger resistor with a bigger resistance, right? And we'll talk about what that looks like. But I'm actually basically done here, right? I solved this equation for I get I1 is equal to VB divided by the sum of the resistors, like so. And I can do the same thing for I3, right? I3 is going to be equal to VB divided by R3. And if I want the voltages, I just multiply those I's by the corresponding resistances. So for example, the voltage across resistor 1 would be R1 times I1, which is VB over R1 plus R2. And similarly, V2 is going to be R2 times VB over R1 plus R2. You can do some quick sense making here and notice that the units are working out here, right? We've got a voltage times a resistance over resistance for both of these voltages. You can also think about what would happen in a limiting case, a special case here, right? So for example, if I didn't have resistor 1, if I set resistor 1's resistance to 0, which physically would be replacing it with a wire, then I would expect all of the voltage to drop over R2. And when I plug that in, I see that the R2s cancel out. Right, this R1 goes away, the R2s cancel out. On the other hand, if I put R1 equals 0 in for this one, I just get a big old 0, right? Because I don't drop any voltage over an ideal wire. So this works out really well for our special cases. The last thing that I want to do here is I want to back solve for the current through the battery. Didn't actually ask you to think about that one, but I wanted to figure it out anyway. So I'm going to add together these two currents right here, I1 and I3. And you'll notice one interesting thing, which is that both of those currents depend on the battery voltage. So I can factor that out. So I'm looking for the battery current. This is going to give me the battery voltage times, and I might do this freehand, 1 over R3 plus 1 over, and I'm not going to write R1 plus R2 here. I'm just going to write R12 for now. Right, that's R1 plus R2, but I only want to write some. And actually, I can put that on the other side if I really wanted to, right? And write an equation that looks like VB equals IB. And again, I don't want to write 1 over R3 plus 1 over R2. So I'm just going to write REQ for R equivalent. And here again, we see that we can write an kind of equivalent resistance and treat all three resistors combined as one thing that has some new resistance that you can figure out from the rest of them. I'm going to show you what that looks like over here on the other side. So here are your rules for adding up resistors in series and parallel. The series one is pretty straightforward. You just add the resistances together. The parallel one is a little trickier. You have to add the inverses of the resistances together. That's actually an old style formula called a geometric mean, I think. You might have seen it before when we did optics with focal length and distances. I don't know if there's any other context where you might have seen that, but that's a way that we can handle resistances. Of course, we can add together more than two resistors. In fact, we did that here, right? We first added together the two resistors in series, and then after that, we're able to write down the parallel resistors and kind of collapse them. And you can do this with arbitrarily more resistors if you want to. We won't usually have really big circuits like